dynamic information flow tracking. It will be given by Subarno Banerjee.
Thank you. Good morning, everyone. I'm Subarno from the University of Michigan, and I will talk about a hybrid program analysis technique that can accelerate useful dynamic analysis by making assumptions about the program's dynamic behavior. So dynamic analysis incur huge runtime overheads that limit them from being deployed. For example, even a simple analysis like if you want to track how information flows through execution, say to enforce some kind of security or privacy policy. For example, here in the program, let's say secret is a sensitive information, and that should not leak through the print statement. To check for this, a naive dynamic analysis will have to instrument each instruction to check whether either of its operands are tainted or marked as sensitive, and then compute if the resultant should also be marked as sensitive. So this obviously incurs a lot of tracking and checking overhead and slows the whole program down. Now, a static analysis can help elide some of these dynamic monitoring operations because it can reason, for example, using data flow analysis, that not all of these operations ever propagate taints. So it can remove those operations. Now, in order to be sound, traditional static analysis considers all possible program states. But since computing this exact set of behaviors is undecidable, it also includes a lot of infeasible states, which makes the analysis imprecise and unscalable. Optimistic hybrid analysis tries to tackle this imprecision problem by considering a few tested program states and then predicates the static analysis by assuming invariants learned on those states. So these invariants are properties that are otherwise hard to prove statically, but almost always hold dynamically. And by assuming them, the predicated static analysis significantly reduces the state space, thereby making the analysis more precise and scalable. But special care is still needed to ensure soundness when a state outside of the predicated state is ever encountered dynamically. So optimistic hybrid analysis works as follows. It observes a few executions of the target program by running it on profile inputs and gathers invariants that likely hold true in most dynamic runs. The static analysis then simply assumes these likely invariants, predicating its state space, significantly improving precision, and thereby it is able to elide many of the dynamic checks. The optimized dynamic analysis then executes, and additionally, we need to add dynamic checks to check for the invariant violations and a mechanism that somehow recovers the soundness of the analysis. So the question is, how do we recover the analysis? Well, in prior work, they just roll back to the beginning of the program and re-execute with the unoptimized analysis. While this solution works for offline postmortem debugging kind of analysis, we cannot tolerate rollbacks on live production systems. So there are two major problems with having rollbacks. Because you are doing this whole program analysis, it is very difficult to bound the window of the rollback because an invariant failure anywhere could essentially affect in an unsound optimization as far as at the beginning of the program. So you have unbounded rollbacks. And even if you could bound the rollback window, supporting for a rollback requires additional checkpointing and logging overheads, even during normal execution other than the actual rollback and replay costs. So in order to apply optimistic hybrid analysis for live production systems, we absolutely need to eliminate the rollback problem. So instead, we want that if an invariant ever fails, the recovery mechanism should simply switch to the conservative analysis and be able to continue from there forward. So to enable forward recovery, we make the following observation. If a monitor is such, if the predicated static analysis can prove that a monitor is such that it never updates the analysis metadata state, it essentially becomes a no-op. So for example, if we have a operation of this type y equals public, where the value public is never really sensitive or tainted, the taint monitor for this operation will not modify the taint set. It remains unchanged. So if we were to elide this taint monitor, even if we encounter a future invariant violation, this will not require us to roll back to correct the effect of this elision, because executing a no-op monitor has the same effect as eliding the no-op monitor. So this is our key observation, and we see that by elision of these kind of no-op monitors is safe because it maintains the exact metadata state as in a conservative analysis. So we limit our analysis to only do these kind of safe elision optimizations. So we apply our technique and evaluate for information flow security tracking on 2 applications, a mail server and a web server. And we see that it's a lot faster than tracking that is optimized using conservative static analysis. And finally, I want to talk about a new application that we are working on for memory safety. Temporal memory safety checks for initialization checking, use after free or double free kind of errors incur significant runtime overheads. Garbage collection, automatic garbage collection is a way to enforce temporal memory safety and at the same time alleviate the programmer from the burden of explicit memory management. And we want to support this for legacy programs written in C. And essentially, garbage collection needs to track all live pointers. But in the absence of runtime information for type information for C, the problem even becomes which values are pointers, to identify what values are pointers. And existing garbage collection solutions for C are conservative in the sense that they treat any value that resembles a pointer, that looks like a pointer, to be a pointer, and then goes from there. This obviously leads to retaining some extra memory, but more importantly, this is not safe. C is not type safe. So as soon as you convert a pointer or cast a pointer into an integer, all bets are off. So instead, you need to track information flow from all pointers. And this is where we use our optimistic analysis to efficiently track information flow from pointers. So to summarize, optimistic hybrid analysis can make dynamic analysis much faster by assuming likely program invariants. We use this to improve information flow tracking on live production systems. Prior work has already applied this to offline debugging kind of analysis like data rest detection and program slicing. The key techniques that we use to improve optimistic hybrid analysis are that we eliminate the rollback problem by limiting to only safe elision optimizations. And we also improve the profiling methodology by leveraging existing software test suites. And for future work, we are looking at applying this for temporal memory safety and language level sequential consistency. So I also have a poster, so please drop by for more details and discussion. Thank you.
That's nice that the analysis figures out that it can always continue if an invariant fails. Like if an invariant turns out to be not true. Is there any way to continue with like a partially optimized analysis after that point? Like it seems like there might be a lot of computation to do at that point to remove some of the instrumentation.
Yes. So this slow path is actually a partially optimized analysis, which is optimized by not assuming any of the optimistic invariants. So you still fall back to the, so in our current solution, you fall back to the conservatively optimized analysis, which does not assume any of the profiled invariants. This is only a black and white solution, but you can have multiple shades of gray in between, where if an invariant fails, you deduce which optimizations are unsound, rendered unsound, and then only disable those optimizations.
Okay, so that is an option. Okay.
Yes.
Okay. Other questions?
All right, thank you. Please stop by at the poster.